All right, welcome back to CS 194-15. So we're going to be starting on, more into the parallel computing after last week's lecture and lab last week. And today I'm going to talk about something called the roofline model, which is a performance model that you can use either for single processors or for shared memory multiprocessors. It actually has extensions to GPUs and other things as well. And I want to thank Sam Williams for producing many of the slides. And if there are errors in there, they're probably mine and not his. But okay, so first of all, what is a performance model? So it's a formula to estimate the performance. And the performance can mean things like the running time, which is what we'll often be using for. It could be bandwidth, could be the memory footprint that's being used. So something that how much memory does a particular application use for a particular input. It could be something like the percentage of peak or the energy use of the machine. So you can have a model that will try to capture a number of different characteristics of your application. Now, if we want a formula, we use a formula then to estimate the performance. So that's really what the model is. So you have seen big O notation in other classes already and in this one. And that's an estimate of the performance. It's a performance model that tells you roughly how the computational cost grows with the size of the input. You've seen more detailed formulas. So we looked at something like this formula, I think back in lecture 2, maybe. It was the number of floating point operations times the time per floating point operation plus the number of memory operations times the time per memory operation. And we also looked in one of the homeworks at the cost of moving data from the disk to main memory, which was captured as opposed to having a single constant cost per each memory operation or per word. It has both a latency cost, which is fixed per transfer, and then the cost per byte. So X over which is the number of bytes divided by the bandwidth. So these are some of the examples that we've seen for time. And we're going to be mostly talking about time today as well. Why do we want to use a performance model? Why not just measure the performance of everything? And we use performance models to help us understand more about the performance. Sometimes it's because we don't actually have either the hardware or the application written yet, or whatever it is that we are trying to understand. So for example, if you're trying to understand, should I buy an AMD processor or an Intel processor? Is there a model that you can use to estimate how those will perform? Well, you can look at the hardware specs and you can say, oh, this one has a faster clock rate, this one has a wider vector unit, but what does that mean for your application? So a performance model might give you a better estimate of how those two processors might perform in your application. If you're trying to decide between writing something in C++ and writing something in Python, you might use a performance model to say, well, the cost of a let's say writing some small program, let's say dot product in Python has a certain cost, and writing it in C++, not the writing of it, but the running of it in those two languages has different costs. Writing it is a different thing you could try to measure, although it's much harder. So you can look at try to estimate the cost of a larger application by measuring some of the performance of some of the primitives. You can also look at trying to model the cost of a compiler, the difference between using the GCC compiler or using the Intel C++ compiler. Much harder to model. As you've seen, the compilers can be very mysterious in exactly what they're doing and when they're doing various optimizations. Another reason that we want to use a performance model is to help understand what the performance bottlenecks are. This is some data taken from one of my graduate students who is working on a genomics application, and there's actually, I think, 4 different colors in each one of these bars. Doesn't matter for this class what they are, but what we're seeing is that really the only thing that matters is this yellow piece, which fortunately is the computational part of it, not the communication part of this application, at least on this particular input and on this particular hardware. And so what that says is that obviously the only thing you need to speed up is this yellow part. Now this is taken from this is not a performance model, this is taken from an actual run of this on a number of different size machines. But what you could do is look at the complexity of this and say, well, this computation that's in here is order n squared. And in fact, you're doing it multiple times. And so it can almost be up to n to the fourth, although it's not quite that naive in terms of how it's implemented. Whereas a lot of these other things are going to be closer to linear. And so the performance model might help us decide, even before we've written the application, that the thing to work on optimizing is going to be this yellow piece. So you also might use it to decide between whether you need better software, a better implementation of your algorithm. So you can sometimes tell that by figuring out whether if you're doing something somewhat recognizable, so you have a loop that's mostly looking like matrix multiply, but it's not performing like matrix multiply, that would suggest you probably need a better software. You either need better code that's being generated from the compiler, you might need to tile the loop, you might need to do something else. If you are actually running at something pretty close to the hardware performance, then maybe you need better hardware. Or if you've got the best hardware you can, maybe there's some way you can come up with a better algorithm so that you can change the relative cost of things. And finally, and perhaps most importantly, I think it's very important to have a performance model so that in the back of your mind, if nothing else, even if you haven't formally written it down, but we will be writing it down, so that you can tell when you're done optimizing. And this was a question that came up in Piazza many times in homework 3, and homework 2 as well, which was, how do I know if my answer is good enough? And frankly, we didn't answer that because we were expecting somewhat higher results. If you look at how fast some of the implementations of matrix multiply go on the KNL hardware, we were expecting more like at least 50% of peak. Some of them will run as high, at least on certain matrix sizes, as 80% of peak. We knew that people were getting much lower numbers than that, so we're a little worried about giving you an absolute target that might have been much too aggressive. But it's very useful to know, and percentage of peak can be a good way of doing that. That's one model. But there are applications in which there's no way that you will get anywhere close to 100% of peak. And so you need something more sophisticated to tell you what to expect on a particular application. Now, so far in this class, we've looked at 2 types of machines, and just briefly at the second one, but you're in the middle of that right now. But we've looked at single processor machines, which roughly look like a processor connected to a memory, and it's got a cache, and then a shared memory machine where a bunch of processors all talk to the same shared memory. And the roofline model that I'll be describing today can really capture both of these pretty well. So what are the critical performance issues on these? Well, the 2 critical pieces of information are how fast is the processor, which we can calculate by looking at the clock speed and the various types of parallelism that are on the processor, which you did in the quiz, and you looked at in various labs, and I think in the lab assignment as well. So you can multiply those together and figure out what is the speed of the processor. And here, when we got multiple cores, we can also multiply by the number of cores, which I guess you also did in the quiz. But the second thing that we know is very important is the speed of memory. Now, there are other things like the size of the caches and things that are going to also be important, but certainly the speed of the memory system, both the memory latency, which I think goes back all the way to maybe homework 1, where you were writing something where you're jumping around through an array, and the bandwidth can be very important. And we had a homework where you looked at that when you were looking at the disk utilization, the difference between something limited by latency versus limited by bandwidth. So a little history of the roofline model. So Sam Williams invented the model when he was a grad student at Berkeley. He was also at the time working at Lawrence Berkeley Lab, and in fact is still at Lawrence Berkeley Lab as a scientist, and still working on variations of the roofline model, in addition to making lots and lots of complicated scientific applications go fast, and looking at hardware and other things. And he had actually done a lot of work on making various applications run fast as part of his PhD thesis, and in particular things like matrix vector multiply, actually the sparse version of that, and a number of other computational kernels, things that look kind of like convolutions that come up in neural nets, although in this case it was stencils, which we'll look at a little bit later. And as he was writing his thesis, his advisor, Dave Patterson, said, well, can you capture all of these different optimizations in some way that helps us understand them a little bit better? And he developed this idea of the roofline model. And I'll have to say that it's a fairly simple idea in some sense, but it captures what people had been thinking about in a number of different ways in a graphical format that makes it very intuitive and is very helpful and has become extremely popular. So in this paper, which was written by Sam and Andrew Waterman and Dave Patterson, in the communications of the ACM, this was following some earlier papers that described the roofline model. This paper alone has over 1,700 citations. So a lot of people have referenced this work. To me, I think one of the other things is that people now, and I do this, talk about roof lining in applications. So it's not just a roof line, but the act of going and analyzing it in a certain way has become a verb that people will suggest you do when you're looking at the performance of an application. What's in the roofline model? Well, there's going to be three pieces of it really, two about the machine and one for the application. We've really already talked about the two characteristics of the machine that are important, the arithmetic or computational performance. So for example, the number of floating point operations per second, although you could use integer operations and you could use single or double precision floating point, you do want to be consistent on a particular instance of the roofline model, which of those you're using. And that's going to be determined by the clock speed and the parallelism, as I said before. Now, the memory bandwidth is the other key piece, and so that's going to be in bytes per second. We're not actually going to directly put on the roofline model the latency, and so what this means is that we're looking at the best case. So how do we think about that? We know that latency in general is much slower than the bandwidth in terms of the cost per byte that's moved. If you're just going to go and read one byte in the middle of nowhere, sort of as a separate point, then that latency cost will be much higher. And you know a lot about the caches and the memory system and how it moves lines and things like that, which explains why the two things are different. So we'll be looking at the best case. And in fact, the roofline in general is going to give us sort of a best case, an upper limit on the performance. At the application level, we're going to look at the computational or an arithmetic intensity and the balance, that is the number of floating point operations per word. It can also be floating point operations per byte, or if you're using something like integers, could be integers per byte or per word. We tend to use word because it tends to be easier to count in your mind, but a lot of other people in a lot of other papers actually will use bytes rather than words. When we talk about words, we have to be careful, just as we are when we talk about floating point operations. Do you mean single precision or double precision? Or now, for example, in some of the latest processors, or at least designs, they're talking about 16-bit, so narrower floating point. And certainly with integers, you can have both long and kind of regular integers and short. So you do have to make sure you're careful about that. So what does the roofline look like graphically? I said as a graphical model, and it's going to have the two axes are going to be computational intensity on the x-axis and the gigaflop rate that you're achieving in the application, the attainable gigaflop rate on the y-axis. And so it's fairly simple. Now it's important to notice that both of these are log scales. And that will be important for a number of reasons. One is, as a performance model typically does, it's going to approximate the details. And in this case, what it means is that some small factors of performance are not going to be very visible on this plot. And that's okay, because if we're looking at things like, should we stop optimizing the code? Most likely we're looking at things like, are we within a factor of 2 of the best that you can do? Once you're within a factor of 2, maybe it's time to stop. Now, there certainly are people that will worry about whether you're 70% or 80% or 90% efficient, but the log scale will sort of capture what's important. And it's also going to be important in terms of how we draw the roof line. So the first thing that we can do is to draw the flat part of the roof, and these are going to be based on the peak performance of the hardware. And in a naive performance model, the peak performance will just be one number. And so the axes, just to say again, is the computational intensity on the x-axis and the attainable gigaflop rate. So the performance in gigaflops per second, I should say, on the y-axis. And so the peak performance is what we have written down and you've calculated before. There was sort of a tricky question on the quiz. We asked what would happen if you were implementing something like I believe it was just a sum operation, and you were using a machine that had a fuse multiply add instruction. And the thing that's important to recognize is that with a fuse multiply add, you can only get that factor of 2 increase in performance if you have a mixture, an equal mixture of multiplies and adds that dominate the code. If you're doing a bunch of other things, such as divisions or non-floating point operations of various kind of integer operations that don't use the FMA, you're not going to be able to take advantage of it. In particular, in that question, you only were doing additions, not doing multiplications. And so it was just making sure you recognize that an FMA will cause you to run at half the performance. And because it's a log scale, here's the peak performance in this hypothetical machine at 64 gigaflops. And then if you've got an application that's only got additions in it, you're going to run at half of the peak. If you don't have SIMD operations, let's say that you've got a 2-wide SIMD, so you don't have, and these things are not, you have to look at them somewhat separately, but if you don't have SIMD units and you don't have multiply add instructions, you'll be down by a factor of 4 if you have a 2-wide SIMD. And instruction level parallelism, we haven't really talked about a lot in this class, but you certainly learned about it in 61C. And it was one of the things that the compiler was doing in general when you were optimizing your loops for register blocked matrix multiply. I was trying to make sure that it's actually going to be able to issue those instructions in parallel. And you saw that sometimes when you unrolled the loop, for example, you would encourage some level of both symbioization and sometimes ILP, instruction level parallelism. So these roof lines will tell you that you are guaranteed to not run any faster than, for example, this line right here. If you've got an application that only does arithmetic, it only does additions and doesn't do any multiplications, or only does multiplications. And if you have got an application that you're, for example, not using the SIMD compiler flags or optimizations in the compiler, or for some reason that most of your code will not SIMDize, then you will know that you're going to be running down here. Okay, so these will all limit the performance, and it's very helpful to know. And you may know that, oh, maybe there's a way I can rewrite this that would give me SIMD instructions, and then I can move up to one of these higher lines. Or, but if not, then you're going to be limited. So once you get to that line, you can stop worrying about trying to improve the performance of your code. So your code, your general strategy in terms of optimization is to try to move up, of course, in these lines. Now, how good is floating point operations per second as a model of performance? If we just had a roofline model that, well, we wouldn't need 2 dimensions in this case. But here, and this was a graph, this was a plot we looked at before when we were looking at matrix multiply, that's DGEM-M, or what's called DGEM, and matrix vector multiply, DGEM-V. And here's the peak performance. So that's the top of our roof line right here. This is problem size, which actually does give you a little bit of a sense of arithmetic intensity, because if the problem size is too low, then the n cubed over n squared isn't going to give you as much as an advantage. But you'll see that this one levels off. Well, both of them get turned into a flat line here, but this one is a much lower number. And so that's because, of course, DGEM-V, and we talked about this briefly, I think in lecture 2, is only doing 2 floating point operations for every element of the matrix. So even if we ignore the cost of reading the input vector and the output vector, we only have those 2 floating point operations. So here's that matrix vector multiply. I like to draw it like this with the vector that you're multiplying by. So A times X up here and Y over here. And every element that's in the X vector is going to be needed to multiply by everything below it. And in order to calculate Y, we can do a dot product on all of the values of X with all of these blue elements of A to calculate this one value of X. We could actually do it also with what are called DAXBs, which is broadcast this element of this element of X down, multiply it times this entire vector, and do a plus equals on Y, and that will also work, but it will use even more memory bandwidth. And so, but the best case here is going to be 2 floating point operations, or approximately. I'm ignoring the cost of the X and Y vector per word. And this was another question that's come up a few times, and we'll see this again, is when people were wondering about big O notation and the constants in it. So in this class, unlike in say CS 170 and maybe in CS 70, we will often want to retain the constant that's in front of the highest level, the highest term in that expression. So, you know, matrix multiply has a 2 in front of the order n cubed, and that will turn out, as we'll see, to be important for some of these applications. We'll still often drop lower order terms. So if it's 2n cubed minus n squared, we might drop the minus n squared because that won't matter very much, but we will care sometimes about the constant in front. Okay, so so if we're looking at matrix vector multiply, we can assume that the runtime is actually roughly equal to the amount of data move and the cost of moving that data. And so if we assume that that's true, then, well, we don't necessarily, it can be hard to estimate that without having all the details of the cache in order to know exactly what is moving in and out of the cache to the DRAM. But we can approximate it by looking at least as a first estimate, by looking at the compulsory data movement. That is, what is the total size of all the data structures that you're computing on? In this case, if we've got one matrix and 2 vectors in the matrix vector case, and those compulsory misses are pretty good first guess. And then we have to write out, of course, the Y vector as well. And maybe we don't need to read the Y vector in if we're not doing a plus equals, if we're just doing an equals. And so this will give us also a performance upper bound. That is, you can't do any better than reading exactly once all of the data that you need to read in order to perform the computation. You've got to read your data structures to compute on it, and you've got to write the answer. So this performance upper bound is also what we'll see in the roofline model. As you've already seen, by having multiple flat parts of the roof, we can get better upper bounds if we know that for some reason we can't, for example, use a fuse multiply add instruction or a SIMD instruction. But in general, the roofline model is going to bound how fast we can go. Now, I've just shown here what the floating point operations total flops are, so not per second, but the total flops are for things that you've seen before, such as matrix vector, dot product, matrix multiply. You've actually seen n-body. I think it was in one of the homework assignments, and also you've really seen it in disguise in a number of different things where you're looking for all of the common patient IDs, for example, in a list when you're looking for, that's really an order n squared computation. Basically, anything that compares everything to everything is going to be sort of like n-body and this n squared computation, but the amount of data is only order n. And an FFT, I'm just showing because it's got a more interesting formula here. It's an n log n computation on order n data. And we hopefully we'll look at that later in the semester. So if we try to put these two things together, we want to look at the machine balance, and we've talked about this before. The balance is the peak operations for the bandwidth. So the top is floating point operations per second, and the bottom is bytes per second. And so what is typical? So the typical number of floating point operations per second per byte, so flops per byte. So the 2 seconds here cancel out because there's a seconds. I should have written out the bytes per second maybe on the bottom, but those seconds will cancel out. And so we end up with a machine balance number of how many flops per byte does it have. And people will often ask when you're looking at a new machine, what's the flops per byte? And that means what is the rate of floating point operations per second over the rate of bandwidth bytes per second. And so this is a pretty typical number, somewhere between 5 and 10 flops per byte. Notice already that something like matrix vector multiply, you should be a little worried about this because there's no way we can run at close to peak when That's only 2 flops per word, and a word is larger than a byte, so it's going to be much lower than, it's going to be a fraction of a flop per byte, depending on whether it's single or double. And in general, the trend over time is that this balance does not get better. In order for it to get better, you need to have faster wires connecting the chip to the off-chip DRAM, and faster wires are very hard to get because there's a distance, so there's a latency cost, but also there's a limited amount of area around the chip. And whereas the amount of computing you can stuff on a chip under Moore's law kept getting faster, bigger and bigger. You can put more and more transistors on the chip. So just to give you some concrete numbers, the Haswell system at NERSC is 10 flops per byte, whereas the KNL nodes is 34 flops per byte, so much worse than this estimated typical 5 to 10. For that reason, because the Intel designers realized that they couldn't get enough flops per byte, and part of that is the cost of DRAM, so you'd have to stuff a lot of DRAM around it, and part of it is not being able to get enough pins or wires in and out of the processor chip to the DRAM. They added something called high bandwidth memory, or HBM, and that one is much better at 7 flops per byte. And mostly with the way we use the system, this really looks like another level of cache, but nevertheless, it is another level of memory. I'm not going to read through this slide. This is a slide that I showed in lecture 2, but I'm just keeping it in the slides in case you download them for backup, and also this one, which really goes through the details of the arithmetic on how you get the 7 and the 10 here for the Haswell. If you include the KNL, the high bandwidth memory, which is called MCDRAM, then you can get to 7. Okay, so here we are. Now we've got our machine balance, which is going to be that bytes per flop, flops per byte, and then our computational or arithmetic intensity. In most of Sam's papers, by the way, he uses arithmetic intensity, and that's very common throughout, because I work a lot on genomics applications that don't have any floating point operations. I often use the computational intensity instead. So computational intensity, of course, is for the application, the number of flops performed divided by the amount of data that's moved. And so those were those numbers we looked at earlier. So here, and we can actually compute it in big O notation, that sometimes it's constant. And then we've got something that's order n. Now, in this case, this particular chart is assuming I've got an infinite cache. So I'm really just doing my compulsory misses. And of course, we can come up with much better estimates of computational intensity for a matrix multiply if we know how big the cache is. So let's see, and Ben is just clarifying there that a lower number means that there's a high amount of memory bandwidth that's going to be required, and so which means less computationally intense kernels are going to achieve higher performance. So higher computationally intensive kernels will achieve a higher percentage of peak. So, okay. So we can take those arithmetic, that kind of a table, and we can write it out as a spectrum here. So we can have something like our matrix vector multiply here, which is order 1. Matrix multiply is order n in terms of the computational intensity, and body is also order n. It's actually even going to be better than matrix multiply when you take caches into account. And some of the other things here along the spectrum. We haven't talked about sparse matrix multiply or lattice methods, but you can also fill these in along this various spectrum. And so that's what we're going to use for our x-axis in the roofline model. So we're looking for the question is, are we looking for a low balance? That's correct. We're looking for a machine that has a low number of flops per byte required, and an application that has high computational intensity. So here we've got, what we're going to look at is the roofline model. And by the way, the roofline can be used in other things such as the network between nodes and on GPUs and things like that. But here we're going to be looking at it for DRAM. And so what we need to look at here is if we've got just this simple model of a processor, now we're not even really paying attention to the cache, where we've got the CPU performance, and we could have multiple processors in there. We can have multiple cores in there. So it's the whole set of all of those cores in a multi-core system. And we've got our DRAM down here. We worry about the performance of the DRAM in terms of the gigabytes per second. So we can assume that we've got these idealized processors and caches, and we're just going to look at the cold start. That is how much it costs, the compulsory misses to move the data from the DRAM into cache, as I've mentioned before. So what is the size of the data structure sitting in DRAM? How much do we have to move into the CPU? And then how much do we have to write back at the end? And so the running time is the maximum of the floating point time, that is the number of floating point operations divided by the peak, and the number of bytes that have to be moved back and forth, either in or out, divided by the peak bandwidth of the machine. So before, at the beginning, I showed you in lecture 2, we used a different formula. We used a sum for these. We added the two together. Here we're using the maximum. And why are we using the maximum? We're using it because in many cases in the hardware, the floating point operation can happen simultaneously with the data movement. And so the absolute best case that can happen is that they're both happening together. The floating point units are fully occupied, and the memory is moving. Now, in practice, you've got to issue those memory instructions and things like that. So you're going to use some instruction slots for that. But nevertheless, this will give us the upper bound. Is just saying what is the best you can do. You can either be limited by the floating point operations, or you can be limited by the number of bytes. There's a question about DP and and that stands for double precision floating point. Sorry, I was trying to remove those with FPs, but yeah, DP is just another name for floating point, but when it's double precision. So another way of looking at this then is that the operations per second that you can get, the gigaflop rate, the number of floating point operations per second, is going to be the minimum of the peak gigaflop of the machine and the peak bandwidth of the machine times the arithmetic intensity, the number of floating point operations per byte that you're going to do. So that is just because we're now putting the, we're just taking the previous maximum and now looking at operations per time limit as opposed to time as in the numerator. And so this is just gigaflops per second, as I said. Okay, so now we've got our generic machine again. And here I'm just going to have a single flat roof line for a minute, just the peak double precision, sorry, again, that the peak floating point operations or double precision floating point operations per second. And once again, the axes are the attainable gigaflops per second. So we know that we can't possibly run faster than the hardware peak. That's the flat part here. And then we've got our computational or arithmetic intensity. And we look at our machine balance. Let's say that we have a really nice machine, by the way, a machine balance of 4. So what does that mean? Well, that means that we need that we can do, we need to have 4 floating point operations per byte in order to reach this peak. So if we've got anything greater than 4 in our application, we'll be sitting up here, hopefully at the peak, unless we've got something else going on that's going to keep us from that. But we can be guaranteed the memory isn't going to get in the way if we've got we've got an arithmetic intensity of at least 4. We'll be at this flat part of the peak. But what happens over here? Well, we're going to be limited instead because we don't have enough floating point operations relative to the number of memory operations. And so we're going to get a slope that is equal to that's limited by the memory bandwidth. And so that slope is going to tell us that we can't possibly run any faster than the memory bandwidth. And that also gives us some sense of why we don't look at latency. Latency we're well below this if we're actually jumping around through memory or not using all the elements of our cache line. But we can't do any better than if we've got a low computationally intensive problem to run at the memory bandwidth speed. So these are going to be 45 degrees. That's assuming that I've got equal intervals on my axis, that is equal spacing between each one of these points and an equal multiplier between them, which I do. I've got a factor of 2 in both cases, even though that I start at a different point. And remember again, this is a log scale. And so that turns this line into a 45-degree line. Now we will often draw these with different angles, but that's because we'll use different ratios on these axes. But as I'm drawing them here, it's always going to be 45 degrees because there's a factor of 2 in both and the spacing is the same. And this point right here, where the machine balance line intersects the peak double precision floating point line, well, what would it mean if I had an application that's running right here at this performance? That would mean that I have exactly gotten an application that is running at 4 floating point operations per byte. And so that means, by the way, many more per word. So if it's single precision, that would be 8 times higher, but I've got four floating point operations per byte right here. And that means that I'm saturating the memory bandwidth because I'm right here at this diagonal line, and I'm also saturating the floating point operation. So this is perhaps probably not quite attainable on most of the actual hardware, but an upper limit is I've fully saturated both the floating point units on the hardware and the bandwidth, the memory bandwidth of the hardware. So why do less computationally intense kernels achieve higher performance? I think that Ben was referring to the hardware being requiring less computational intensity. So more computationally intense will give us higher performance, because at least a higher potential performance, because we're limited by this roof line. So that will be the next thing we'll try to do, is to move things to the right. So over in this region, we're bandwidth bound, and in this region, we're compute bound. And why is this also important to know in terms of when to stop optimizing? If you're sitting over here in this region, your application, for whatever reason, especially if you're just looking at the compulsory memory traffic for something like matrix vector multiply, there's no point in trying to optimize your vector width or your SIMD units or other things if you're actually sitting right here on the bandwidth limit, because none of that will matter because you're going to be bandwidth bound. So in general, in terms of optimizing, we're trying to move, we can also have multiple diagonal lines for bandwidth, just as we had multiple flat lines for the arithmetic performance. And so if we've got different, we can have, for example, an application that doesn't use software prefetching that will not be able to achieve the peak bandwidth. So surprisingly to me, that even sometimes when you're running at sort of unit stride, sometimes you need to put software prefetches, and hopefully you remember what a prefetch is from 61C. A prefetch means an instruction that says, please load this value into the cache. I'm not actually using it right now, but load it because I'm going to need it in a few cycles. And that's how we'll get overlap between the arithmetic units and the bandwidth, is by issuing things like prefetch instructions. The hardware will often do prefetching for you, but in some cases, you as an application program may have to insert prefetch operations. This is especially true if you're not doing something that's unit stride, that is contiguous through physical memory. If you're going to, say, jump to another row of a submatrix, you saw this a lot in the blocks, that's why copy optimization helped in some cases. If you've got a block and you're going to jump to the next row, then there's all this other stuff that's contiguous in memory that you're going to skip over to jump to the next line. Some of the hardware prefetchers can be very sophisticated and know that if you're always jumping by, say, a factor of 2 or a factor of 4, it will be able to figure that out and will go and load that next cache line for you. But sometimes if you're going to go around a corner or something like that, you'll want to actually issue software prefetches. NUMA, and I don't know if you studied NUMA effects in 61C, but that means that that not all memory is equally fast. on each core. So what would this mean is, for example, on the Haswell nodes on Cori, there's 2 physical sockets. There's 2 chips that those processors go into, and there's memory surrounding them. And the memory on one side, although all the memory is accessible by the processors, the memory on one half of it is going to be faster to access than the memory on the other half in terms of the amount of bandwidth that you can get and latency. And so all of these are things that you might want to carefully optimize for in optimizing your software, is trying to make sure that you've allocated memory on the side of the cores that are going to be computing on it. And so then the last thing you're going to do from, given the shape of the roofline now, is to try to see if you can improve the actual arithmetic intensity or computational intensity of your application. Tiling is the classic thing that you've already done that is improving your computational intensity. So for dense matrix multiply, which you've spent most of the time optimizing, your compulsory misses will give you a computational intensity that's way out here. That is, if you only look at reading the matrices, the A and B matrix once and writing the matrix C once, then you've only got those 3 or 4 if you're doing an update to C writes of all of the four n squared memory operations, as opposed to the 2n cubed floating point operations that you're going to do. But in fact, your cache means that you're going to, and if you haven't tiled that, you're going to still be sitting here. For example, if you've written it as matrix vector multiply, you'll be sitting over here. And so you'll want to tile it in order to move it over and to the right. So here's a couple of examples that I'll look at. The first one is for one of the benchmarks that I may have talked about in looking at how you measure the memory bandwidth of a machine. This is one of the things that we'll do, and it's looking at, is to run this benchmark just to figure out what the bandwidth is. And this is a little OpenMP loop for what's called the stream triad benchmark. It's got these 3 vectors that it's reading, 2 vectors that it's reading, 1 that it's writing, and it's not a plus equals. So it's just got 2 reads and 1 write, and then there's a constant that you're multiplying. And so you can just assume that constant is sitting in a register, so we're not going to worry about the memory traffic for that one constant. But we then get a computational intensity of, in terms of flops per byte, this is double precision, I should have said that, is 0.083. So this is going to be sitting on almost any machine, or way over here on the left, at least any modern machine, underneath the bandwidth limit. And so this is going to, that's why we use this to measure the memory bandwidth of the machine, is because it's guaranteed to be saturating the memory bandwidth. There's just only these 2 floating point operations, and you've got these 3 memory operations in there, 2 reads and 1 write. And so it'll look something like that. Now, here's another example, and this looks a little bit like a convolution that might come up in deep learning, except this is being done on 3 dimensions, and it's called a stencil operation. And all it's doing is really averaging or computing the next value of a point by looking at all the values of the nearest neighbors in a 3-dimensional mesh. So imagine inside of this mesh, and this is hard to see because this is 3 dimensions, we've got our neighbor to the left and the right, our neighbor up and down, and then our neighbor in front and in back. And so we're taking those 6 values plus the value itself. So it's called a 7-point stencil because of these 7 points. And here's a little bit of pseudocode for the inner loop. If you look at this as 7 floating point operations, so we're just adding all of these values together. And then we've got the 2 multiplies here, not very balanced, by the way, in terms of our FMA unit, but nevertheless, our computational intensity in this case is going to be the problem, not the FMA, is only 0.11 flops per byte. Now, it turns out, though, that if you think about what the cache is doing as you're running through a 3-dimensional array, and you may not have thought of this as much as you've certainly thought about 2-dimensional arrays as when you're doing matrix vector multiply, matrix multiply, but in a 3-dimensional array, when you're going through here, some of the values as you're looking above and below you or to the left will certainly be in cache, and the one above you will be in cache, and the ones behind you may also be in cache, and this one will be in cache from the time above when you were accessing the one below. So only one of these values on the right and the one on the left actually as a write are actually have to be written, assuming that you've got big enough caches to hold an entire plane of this 3D matrix. And so then the computational intensity actually is a little bit better. It's 0.44 operations, floating point operations per byte. And so if we put these two things together on the roofline model, we have triad, which was 0.083, and the 7-point stencil, assuming we've got big enough caches, is at 0.44. So they're both under the bandwidth limit of the machine, but here they are at different points. And here's why the leading constants matter, and so that we will sometimes have to not just use big O notation, but really worry about those constants. So what makes this such a useful model? I said that there's over 1,700 citations of this model, and one of the papers about this model. That means there's, by the way, over 1,700 other publications that all use the roofline model, and that people use it all the times. And those are just the ones that were citing that one particular paper, and others might be citing each other and not citing the original paper and so on. So what we're looking for in a performance model in general is something that is simple enough to give us insight, and accurate enough to be useful, that is, to be meaningful, to give us some meaningful information out of it. So if we just said, well, let's look at our peak precision floating point rate of the machine as a model, that is a model, but it tends not to be accurate enough to be meaningful for many problems that we care about, because most of them do not live, they're not computationally intensive enough to be saturating the arithmetic units entirely. And what does it mean to be simple enough to give us some useful input? Well, there was a paper I remember written years ago on an IBM processor by a team at IBM, writing down a careful analytical model that is a set of equations and formulas for all of the details of how all the caches, and I think it was a 3-level caching system, and prefetchers and all of that worked on that architecture, and it turned into many, many pages, like 20 pages of formulas. So now that actually, maybe you would consider that useful. It tends to not be useful because I have to basically write a program in order to evaluate those 20 pages of equations. And so it doesn't really give me any intuition. I mean, sometimes I can plug in some numbers and maybe a number will pop out that says this is what will happen. But at that point, maybe I should have just written the application on the processor and measured it. And so we want this balance between something useful and something detailed and something simple. And so roofline does not capture everything. It doesn't really capture latency in memory. You'll see some things that will be down below the memory bandwidth peak and not on the computational end, because because you can't, because you're actually memory latency bound, you're jumping through memory, for example. The roofline model is basically assuming that you can hide all the latency with things like prefetch operations, or just what the cache is doing already, because it's loading, multiple elements, and so you don't see the latency of each one of those individual elements. So it's a simplifying assumption, and it will sometimes cause you to not be able to understand, you'll have to think harder about why you're not going to hit peak, but in general, it's very useful. And so I'm just summarizing with a quote by a famous statistician, George Box, who says, all models are wrong, but some models are useful. And this will come up over and over again. And I think the roofline model is a great example of that. So it's important to remember that it's not perfect. There are cases in which it will be wrong in terms of telling you exactly how fast your application will go. You will, although you put these posts in at the computational intensity for your application, you will often not be all the way up at the peak, either at the floating point or memory bandwidth peak. But nevertheless, it gives you some idea of how fast you might be able to go in that application, and gives you a sense of when you might want to stop optimizing. So with that, I will end, and thank you very much. Hopefully, if there are any questions, we've got one more minute left. All right, great. Well, we'll talk more about parallelism and multi-core on Wednesday, and we'll see you then. And hopefully you can get started on the homework as well.